All right, in this video, we are going to be deriving the C5h character table. And so the first thing we always like to do here is think about an example molecule. There are a lot of C5h examples. So what we can do is we can think about just a pentagon which has D5h symmetry and know that this isn't a D group. So there's not going to be perpendicular C2s, but we're still going to have that principal rotation axis. That's going to be our Z-axis with the C5. And we are going to have a sigma H because we're a CNH point group. And so we have to come up with all the symmetry operations. Of course, there's always identity. There's going to be that C5 rotation. We can do that C5 rotation twice for not 72 degrees, but 144 degrees. We can do that C5 rotation 3 times and 4 times. And we can't do it 5 times because then we're back to identity, right? 360 degrees, okay? And we also have the sigma H. That's the mirror plane that is cutting through this pentagon. And then lastly, we have all the improper rotation axis. So we have S5. Remember, an improper rotation axis like S5, that's a C5, so 72 degrees, followed by a sigma H. That's a unique thing mathematically. So we have that because we can rotate this pentagon, take this point and take it to this point, 72 degrees, and then flip anything from the top to the bottom. We also have, we don't have any even S5s. And the way I can show you that is if you have some S5n and you do sigma H, that's going to be a C5n followed by a sigma Hn times, right? So like if n is even, sigma Hn is going to be equal to identity. And then S5n is therefore just equal to C5n, which we already have, right? We already did the C5n's. So for example, if sigma H is 2, you do a flip bottom stuff to the top and then top stuff back to the bottom. That ended up not doing anything. So the even values of S5n aren't going to be valid, but an S5 3 times is going to be a new operation. An S5 3 times is equal to a C5 3 times. And since you have an odd number of flips of sigma H's, that just equals to doing a sigma H overall, the even component of it. So you do sigma H 3 times, bottom to top, top to bottom, bottom to top. And that is equivalent to just doing bottom to top, which is a sigma H. And so similarly, we can have a S5 5 times. Can we? No, we can't, right? Because an S5 5 times is actually equal to sigma H, because we did a C5 5 times, which is equal to identity. So then all we have is sigma H. So that's not unique, but we can have a sigma S5 7 times. That's going to be equal to a C5 7 times sigma H 7 times. Well, that's equal to a C5 7 times a sigma H. And what's a C5 7 times? That's a C5 twice, right? Because we do 360-degree rotation for the C5 5 times, and then we still have 2 C5s left over times sigma H. And we actually don't have that operation yet. We had C5 times sigma H1, we had C5 3 times sigma H, and then we have C5 2 times sigma H. And lastly, we have S5 9 times. Again, just doing the odd numbers here. Even numbers we know aren't unique. S5 9 times is a C5 9 times, followed by sigma H 9 times. So that's an odd number. And so it's C5 9 times followed by sigma H. And that equals C5 4 times followed by sigma H. And once we get back to S5 10 times, well, that's the same as an identity. Then S5 11 times is going to be the same as S5. So those are all of our symmetry operations. So now we have to think about how to group these operations. We have 10 operations into classes. And this can be a bit tricky, but to start out, what we do is we know that there's some rules on this. Identity is always in its own class. And then we're going to want to look for mirror planes. The mirror planes are oftentimes going to be grouped together. Well, we only have one mirror plane, so that's going to be by its own class. The rotations and the improper rotations are oftentimes grouped together, but not in these C and H point groups or the CN point groups. And there's a reason for that. The reason is that there's no way to call these things equivalent. So the mathematically rigorous definition is that two symmetry operations, if you can change the axis systems and have them be equivalent, and you can interconvert between those axis systems with some other symmetry operation in the point group, then they're equivalent. So what I mean by that is, for example, C5, you could say is taking this point and going to that point. That would be a C5. But you could also say a C5 4 times if you defined it going the other way, does the same thing. C5 4 times. So you might think those are equivalent, and they are equivalent in, for example, the C5V point group. But in the C5V point group, you have some symmetry element, namely mirror planes, sigma V's or sigma D's, that can interconvert the axis systems that make these two things equivalent. We don't have that in here. Namely, we don't have sigma V's, perpendicular C2s, or sigma D's. So that's sort of the short explanation for why these are all actually in separate classes. So all these are going to be in separate classes, and same thing with all the improper rotation axes. So that's sort of how we would then write that we have 10 classes and each one just has one symmetry element in it. So that's the first step to deriving the character table, is figuring out all the symmetry elements and figuring out what classes they are in.